In this video, we are going to discuss on tutorial 16, topic statics, and we are going to divide into 3 parts. So this is the part 1. So we read the question. Question 1, a uniform lamina is as shown in the figure. So determine the coordinates of the center of gravity of the lamina. B, the lamina is suspended freely from a small hole at A. Draw a figure to show the lamina in its equilibrium position. Okay, we do question A. To determine the coordinates of the center of gravity of the lamina, so we need to find the the mean of the x coordinate and the mean of the y coordinate for the lamina. Okay, so to use the formula for the center of gravity, we need to divide the lamina into two parts. So the first part is the rectangle and the second part is the square. Okay, so the center of gravity of the rectangle, we draw the diagonal, the first diagonal here from this point to this point, and then another one. So that's the intersection. The intersection point will be the center of the gravity of this rectangle. Okay, the coordinate of the center here is half A and A, because given that the width of the lamina is A, here to here is A, so in between will be half A. Okay, next for the square will be we draw the center of the square, and the coordinate will be 1.5 A for the x coordinate, and for the y coordinate will be half A. Okay, so now we can use the formula for the coordinate x, mean of coordinate x of the two bar. Okay, if we use the formula, W is weight of first lamina times the distance, x distance from the origin, which is half A, plus weight 2 times the 1.5 A. Okay, the distance of the square is 1.5 A from the origin, and divided by total of weight. But we cannot use this formula because we don't know weight. Weight is not given. So instead of using weight, we can use area, because weight is directly proportional to area. So weight is equals to mg, and density is equals to mass over volume, where volume is area times the thickness of the lamina. So lamina is a plate where the thickness is the same. So therefore we can use area instead. So combining these two, so the weight is directly proportional to the mass, and the mass is directly proportional to the area. So that's the reason why we can use area instead of weight. Okay, so now we calculate the area of the rectangle here, which is 2A divided by half A. Okay, or 2A divided by A. Okay, 2A divided by 2A multiplied by A for the area, and then the distance is from the center of the rectangle to the origin. Okay, half A, plus for the square, the area is A times the 1.5 A. Okay, distance from the origin. So divided by total of the area. So we simplify this 2A. A times A is 2A squared. Okay, this one A squared divided by 2A squared plus A squared. So we get below here 3A squared. And the top one, we factor out A squared. So bracket become A plus 1.5 A. And we solve, finally we get 5 over 6A. So that's the x coordinate, mean of the x coordinate for center of the gravity. Next, we are going to find the center of y coordinate for the center of gravity. Okay, so we use area times the distance, y distance from the origin. So the area of the first rectangle is 2A squared times the distance center of the rectangle to the origin is A, okay, times A plus. For the square, the area is A squared, and the distance from the origin to the center of the square is half A. So multiplied by half A, then divided by total of their area. So we solve this and we get 5 over 6A. Okay, so that's mean the center of coordinates of the center of gravity of the lamina is somewhere here. So the coordinate will be 5 over 6A and 5 over 6A. Same coordinate for center of gravity. Okay, another method we can find the coordinates of the center of gravity. Okay, by we still divide the lamina into two parts, rectangle and the square. So the first rectangle, we determine the center of the rectangle, and the square also the center of the square, and we join the we join the center of both rectangle and the square. Okay, then we do for uh, we divide into another different part. This is the rectangle and the square on top. Okay, so we determine the center of the rectangle and the center of the square, and we join their center together. Okay, then the intersection points will be same as the previous method by calculation, which is 5 over 6A and 5 over 5 over 6A, coordinate of the center of gravity. So that's the answer using another method. Okay, next question B. The lamina is suspended freely from a small hole at A. So draw a figure to show the lamina in its equilibrium position. Okay, so if we if the lamina is suspended freely, okay, from the hole at A here. So what happened? The line, this line will pass through the hole A there. Okay, so the line the line will join the center of gravity that we determined just now. Okay, so it hang in equilibrium, where it divide the lamina into equal parts, left and right. Okay, imagine you use a string to hang the lamina like this. Okay, next we do question 2. Three forces F1, F2 and F3 acting on a particle are in equilibrium. So write an equation to represent the equilibrium of the forces F1, F2 and F3. And then draw a vector diagram to represent the equation in A. Okay, so for 2A question, the sum of vector will be F1 plus F2 plus F3 equals to 0. So that's the equation using using sum of vector. Okay, for B, drawing the diagram. Okay, if we choose F1 in this direction, F2 and then F3, so the triangle will be using the tip to toe method, so we can get this diagram, the vector diagram. Look at the arrow here, so they follow after one another. Okay, look at the arrow here, so and then back to the original. So this is called tip to toe method from the arrow. Okay, or you actually you can use it's up to you to use which direction for F1, F2, F3. So example, if I choose F1 or F2, F3 in this direction, so you just follow their direction to make a complete triangle using tip to toe method. Okay, and don't forget to label the forces, the vector force. Okay, next for question 3. Okay, a load W hangs from three strings as shown in the figure. Okay, draw a vector diagram to represent the equilibrium of point P, which is acted upon by forces F, W, and T. Hence, find F and T in terms of W. Okay, so we do question A. So this is T. So we represent the force sorry, we represent the uh, tension in the string T here. We draw here followed by F, so horizontal line to the right, to the left of the screen. Okay, then weight is direction is downward, so it makes a complete a triangle, triangle where the arrow is follow one after another. Okay, so the angle T made from horizontal is 30 degrees. So we can use tangent 30 degrees equals to weight divided by F. We use trigonometric ratio. Okay, so F is weight over tangent 30 degrees. Okay, then if we use sine 30 degrees, so the opposite will be weight divided by hypotenuse will be tension in the string. So tension in the string is equals to weight over sine 30 degrees. Okay, next, okay, so this is for question B, find F and T in terms of W. Okay, so the question done. Next, we go to question 4. A traffic light of mass 46 kilogram is suspended by a cable as shown in the figure. Okay, what is the tension in each side of the cable? So this is the cable separated by the angle 120 degrees. The mass is 46 degrees. Okay, we draw the free body diagram. Okay, the Cartesian plane and the tension in the string. Okay, both string T, another one also T, they have same tension, and another force is weight uh, of the cable. Not cable. What? The traffic. Okay, the traffic light. The weight of the traffic light. Okay. Okay, so now the free body diagram just now we draw. So the weight is mg. So the mass is 46 times the g, 9.81. Okay, second step we are going to use rotational equilibrium. Okay, not use in the solution here. For rotational equilibrium, not needed. So we use the forces along x and forces along y. So we draw the forces along x. So t, we have component t cos 30 degrees and t sin 30 degrees. Another t also the same. We have component t cos 30 degrees and t sin 30 degrees. Okay, so the left and right t cos 30 degrees is equals to the left t cos 30 degrees. Okay, these are equal because the traffic light is in equilibrium. And then the top, the y from the for the y axis we have t sine 30 degrees and t sine 30 degrees left and right side, so we total them up for upward direction and then minus the weight downward direction, and they are balanced, so equals to 0. Okay, now we can substitute the weight into here, so we solve for t. Okay, so the answer is 451 Newton. Tutorial 16, topic statics, part 2. Okay, the first question, continue from part 1. So this will be question 5. A 3.0 kilogram mass is held stationary on a smooth plane which is inclined at an angle of 30 degrees to the horizontal by a rope as shown in the picture. So calculate the tension in the rope and the normal reaction of the plane on the mass. Okay, so we choose Cartesian plane where x-axis is along the plane and the y-axis is perpendicular to the plane. So the rope has tension T, and another force is mg by the weight of the weight of the mass. And another one is reaction. Another force is the reaction by the surface plane. Okay, so the angle here is 30 degrees because this is similar triangle. And then we can resolve the component of mg. So becomes mg cos 30 degrees for the y component, and the x component of mg will be mg sin 30 degrees. And because of this mass is equilibrium, so that's mean T is equals to mg sine 30 degrees. We substitute the mass 3 kg, G 9.81, sine, and then sine 30 degrees. So the answer you can calculate by yourself. So that's the tension in the rope. And then to determine the normal reaction of the plane, we use R equals to mg cos 30 degrees because the mass is in equilibrium. So therefore R is equals to the mg cos 30 degrees. Okay, so we substitute M 3 kg, G 9.81, then cos 30 degrees. And the answer here will be reaction by the plane, okay, on the mass. Okay, that's number 5. Okay, we do question 6. A particle under the action of 4 forces F1, F2, F3 and F4 is in static equilibrium. So write an equation to show the relationship between the 4 forces and then draw a diagram to represent the equilibrium of the forces. Okay, so the relationship between the 4 forces will be uh, F1 plus F2 plus F3 plus F4 equals to 0. So we use sum of the vector to show their relationship. Then for question B, draw the diagram to represent the equilibrium of the forces. So we draw F1, F2, F3 and F4, and be careful that with the direction must follow after one another of the forces. Okay, back to the origin. So the direction of F1, F2, F3, F4 is up to you to draw which direction. Okay, question 7. Three forces F1, F2 and F3 act on a point as shown in the figure. Okay, draw to scale a polygon of forces to find the magnitude and direction of the forces F4. So point O is in equilibrium. Okay, so you are given F1, F2, F3. So we are going to find the fourth force for question A and B. So we do question A first. So we need to draw into scale. We change to the drawing. We need to use a ruler. Okay, so the ruler we draw. You can start with any force. Let's say we start with force F1. F1 4 Newton. So 4 Newton. So that's mean we draw 1, 2 and 3. Okay, into scale. So 1. So that's mean we have 1 and then 2 and then 3. Okay, so this is represent F1. Okay, oh sorry, 4 Newton. So we need to add one more. Draw one more line. Okay, so that will be 4 Newton. Okay. Okay, next we for this force 1 followed by F2 3 Newton. So we continue drawing 1 centimeter to represent 3 Newton. So we have 1, okay, 2 and then 3. Okay, so 1, 2, 3 represent F2, which is the scale 3 centimeter to represent 3 Newton. So direction is upward. Lastly is F3. The angle is F2 done. So the angle is 143. So 143. So we need to turn around here. Okay, so 143. The angle will be we use 180. Okay, minus 143. So the angle is 37. Okay, so the angle is 37. So this is 36. Okay, 36. Okay, so 37. Okay, about about this, okay, about that angle. Alamak. Okay, 37. So we draw 2 Newton. Okay, 2 Newton. Uh, okay, 2 Newton starting from 1 centimeter and then 2 centimeter. Okay, so that will be 3 Newton. This is F3 equals to 2 Newton. Okay, so let's check correct or not. F1, so F1, okay, 4 Newton, then upward followed by 3 Newton, and then followed by 3 Newton, so 37 degrees from horizontal. Okay, the direction is down here. Okay, lastly is to determine F4. So F4 will be, if I choose another color, so we can measure F4. Okay, so this line will be F4. Okay, then you can measure using a ruler. So what will be the angle, the line here? So it's about one. Okay, sorry, one, two, three. Oops, okay, not right. Uh, so it's equals to the 3 Newton. So F4 is equals to the 3 Newton. So that's our answer. And the direction of F4 is downward, follow. Because this is tip to toe method. So look at the arrow. So the arrow here follow one after another. So this is F1 4 Newton, F2 3 Newton, F3 2 Newton, and finally F4 we use the scale just now, it is equals to the 3 Newton. So that's the answer. Okay, next we do B. Okay, next we are going to draw diagram, vector diagram for B into scale. So we start with F1. F1. So use ruler. So we start with F1 3 Newton. So we draw 3 Newton, that means 3 centimeter. 1, 2, 3. Okay, so that is F1, 3 Newton. Okay, next followed by F2, 60 degrees from horizontal. So we turn around the ruler until 60 degrees. Okay, so we draw 6 Newton. 6 centimeter. 1, 2, 3, 4, 5, 6 centimeter. So this will be F2, which is equals to 6 Newton. So draw the arrow. Okay, lastly F3. F3 is 85 Newton. So F 85 Newton, the angle here will be, so we need to find this angle. Use calculator. 180 is a straight line, so minus 75, and then minus 60. Okay, so 45 degrees. So that's mean the angle here is 45 degrees. Okay, so you turn the ruler until 45 degrees. Okay, so now to draw the 8.5, so not enough space, so I need to bring this down. Okay, so draw until 8.5. So one, oops, okay, oh, we turn that to 45 degrees first. Okay, done. So 8.5 will be 1, 2, 3, 4, 5, 6, 7, 8, then 0.5. Okay, so this is F3, okay, 8.5 Newton. Okay, then lastly the F4 will be joining the F3 to back to F1. Okay, so now it's too large. Okay, it's too large. So if too large, you can make the ruler. Okay, you join that one. You join the two. So it's about 90 degrees, vertical, almost vertical. So you draw the line joining. So if you draw properly, you can measure the F4. Okay, this is F4. Okay. So the F4, you can find out by yourself. What's the magnitude of F4? So joining the line together and measure using your ruler. Okay, so if you draw properly, I think you can get this one 90 degrees. Okay, I almost got 90 degrees. Okay, so you can do that on your own. So that's how to get from F4 by drawing into scale. Okay, so that's all for part 2. Okay, next is tutorial 16, topic statics, part 3. Okay, continue with question 8. A uniform meter rule of weight 0.30 Newton is pivoted at the 40 centimeter mark and a load of 0.60 Newton is placed at 20 centimeter mark. So explain whether the meter rule is in equilibrium. And then where must the load of 0.60 Newton be placed for the rule to be in equilibrium? For question C, what is the reaction at the pivot when the rule is balanced? Okay, we do A first. So given 20 centimeter mark for 0.60 Newton and the distance of the pivot here is 40 centimeter from the end. Okay, pivoted at the 40 centimeter mark. Okay, there. Okay, next, the weight of the meter rule is 0.30 Newton. So the weight, the direction of the force will be in the middle. So the ruler is 1 meter. So that's mean the 0.30 mark at 50 centimeter. Okay, center of the ruler 50 centimeter. So the direction of 0.30 Newton is downward. Okay, so now from here, we need to check whether the meter rule is in equilibrium. Okay, so another force that we didn't mention here is the reaction by the pivot here. So we choose fixed point here. So this reaction we don't know. So that's mean we choose the fixed point here. Okay, for this 0.6 Newton, okay, the moment will be mass force time distance. So the force is 0.60 Newton times the distance from the fixed point is 20 centimeter. So convert to meter. So this is moment about the fixed point. We get 0.12 Newton meter. Then for the ruler itself, okay, the moment will be 0.30. Okay, the weight of the ruler is 0.30 and the distance from the fixed point is we have 40 here, 50, so that's mean 10 centimeter. So the ruler, center of the ruler is 10 centimeter from the fixed point. So convert to meter. So we get moment about the fixed point for the ruler is 0.03 Newton meter. So compare these two, one is anti-clockwise, the other one will be clockwise. If the fixed point we choose here, so this 0.6 Newton we make the ruler to rotate anti-clockwise, and the ruler itself we rotate clockwise because of the weight, center of the gravity of the ruler is here. So they are not balanced because they are not the same. So that's the answer for question A. Not balanced because the clockwise moment is not equals to the anti-clockwise moment. Okay, next we do question B. So question B, where must the load of 0.60 Newton be placed for the ruler to be in equilibrium? Okay, so we don't know the distance, so we just put x. So this is value. This is variable x that we are going to find. Okay, so again we choose the fixed point here because we don't know the reaction force. So we just choose fixed point at the the least information given. So r we don't know, so we choose the fixed point here. Okay, so we use also moment, and the total of the torque will be equals to 0. So we choose rotational equilibrium, clockwise as positive, clockwise as negative, and anti-clockwise direction as negative. Okay, for 0.60 Newton, the weight here, the distance we don't know yet, so we multiply by x. Okay, for the R is where the fixed point is, so no need to put also can. Okay, another one is 0.30 Newton. Okay, this force will make the ruler move in clockwise, so that's mean the label we put is negative. The sign is negative. Okay, times the distance just now from the fixed point is 10 centimeter, so convert to meter. So you can solve for x. So I repeat again, positive for anti-clockwise and negative for clockwise. So we solve for x, we get 0.05 meter. So that's mean 0.05 meter is measured from the fixed point. So if measured from the zero end of the ruler, so it will be 35 centimeter or 0.35 meter mark. This is 40 centimeter, so x is 5 centimeter or 0.05 meter. So that's mean the 0.60 Newton must be put 35 centimeter mark on the ruler. So that's the answer. Now we go to question C. So there we must put there. So for question C, what is the reaction at the pivot when the rule is balanced? So we are going to find the reaction. Where we choose the fixed point just now. Okay, so therefore we choose the fixed point at the end of the ruler because we are going to determine R this time. So R is the reaction bar at the pivot here. Okay, so we use rotational equilibrium where total of torque is equals to 0. Okay, so moment about fixed point here will be good. So 0.60 is times the 35 centimeter, convert to meter. Okay, this is where we put just now for the whole system to be equilibrium. So 0.60 times 0.35 meter. And it is negative because the ruler will rotate clockwise. For if we choose the fixed point here, so the ruler here will rotate clockwise. Okay, next for the R, we don't know, so we just put plus R times the 0.40. The distance R from the end of the ruler is 40 centimeters, so convert to meter. And lastly 0.30, the sign is negative because it will make the ruler to rotate clockwise, so that's why we put sign negative. The distance from the end or the fixed point is 50 centimeter, convert to meter because the fixed point we choose at the end of the ruler. Okay, so now we solve for R. Okay, so we get 0.90 Newton. So the reaction at the pivot is 0.90 Newton. So that's the answer. Okay, now so actually we have another method which is simpler because we can use translational equilibrium. Okay, to use translational equilibrium, we just uh, uh, total all the upward and downward. So downward will be negative and upward forces will be positive. So R is we are going to find R. So R is upward. So R minus 0.60 because direction is downward, minus again 0.30 because direction is downward. Then the total will be 0 because the system is in equilibrium. So we solve this, we get the same answer, 0.90 Newton. So using this method, using the translational equilibrium is more easier. Okay, it's easier. Okay, so the result answer will be the same. Okay, so now we do question 9. The figure below shows a uniform rod of weight 160 Newton hinged freely at point O on the wall and supported by a wire PQ. The tension T in the horizontal wire is 80 Newton and the reaction on the rod at 0 at O is R. Okay, so copy the figure and show the forces. Okay, so we copy the figure. Okay, the direction, the tension in in the string. Okay, we label as T. Okay, then weight from the rod downward, and the reaction by the wall is R. Okay, so now that is all the forces that act on the rod. Okay, now we are going to draw the vector diagram for the forces. Okay, for the forces to be for the system here to be equilibrium, so the vector diagram will the what you call this forces, the arrow will be a complete triangle where the direction of the arrow is follow one after another. So we start with weight downward and then follow by the tension in the string, and then lastly is the reaction by the wall. So reaction by the wall, we join the whole triangle because all the forces is equilibrium. So we must join all the arrow to make a complete triangle, and the direction of the arrow is follow one after another. So this is the vector diagram for equilibrium. Or you can start with T also can, so followed by weight and then followed by reaction. So both actually same can the answer is accepted. If you join these two triangle, it will form a parallelogram. Parallelogram method. We can use parallelogram method also to draw the vector diagram. Okay, next we are going to calculate the reaction R on the rod by the wall. Okay, so to calculate the reaction, we use the triangle just now. Okay, so the weight is given, okay, 160 Newton, and the tension also given 80 Newton. So we can calculate reaction using Pythagoras theorem. Because this is right angle triangle, the triangle form is right angle triangle, so we can straight away use Pythagoras theorem. So that means the reaction will be square root of 160 squared plus 50 squared. The answer is 179 Newton. So that's the answer. Okay, for direction of the reaction, we use trigonometric ratio. So the theta will be tangent theta opposite is 160 divided by 80. So the angle is 63.4 degrees. Okay, from the horizontal. So that is the direction for reaction force. Okay, and lastly, question 10. Define a vector quantity. So vector quantity, what is vector quantity? The physical quantities for which both magnitude and direction are defined distinctly are known as vector quantities. Okay, question B. Okay, from the diagram below, the object here is 5 kilogram. So calculate the tension in each of the cables. So this time, the string is not balanced. The string angles, the cable tight is not balanced. One is 60 degrees and the other one is tight 40 degrees. Okay, from the horizontal. Okay, so first step, we choose Cartesian plane and we label tension 1 from the first string, tension 2 for the second string. They are not the same this time because angles is not the same. Okay, then lastly is the weight of the object, traffic light, I think, traffic light. Okay, street light, street light. Okay, so mg, the weight is mg. So the component of T1 will be T1 cos 40 degrees and T1 sin 40 degrees. For T2, T2 cos 60 degrees and T2 sin 60 degrees. Okay, label the component of T1 and T2. Okay, next, we total up all the forces along X. So we have T1 cos 40 degrees minus T2 cos 60 degrees because one is left, one is right. So one positive, one negative, and they are equals to, total them up and they are equals to 0 because they are in equilibrium. So total of forces will be equals to 0. Okay, next, these two. Okay, next, along Y. Along Y, we have T1 sin 40 degrees plus T2 sin 40 degrees. Then minus mg because mg is downward. T1 and T2 sin 40 degrees. The other one is T2 sin 60 degrees is upward. So positive. So we form two equation. For the first equation, we get T1 T1 equals to 0.6527 T2. So we substitute into the second equation. The T1 here, we substitute into the T1. And we solve for T2. Okay, so we get T2 equals to 38 Newton. So at final answer, then we round off to two significant figures. So don't round off too early. Okay, so that is T2. So for T1, you substitute T38 into here. So we get T1 equals to 25 Newton. So that's the answer, tension in each of the cables. Okay, so that's all for uh, tutorial 16, topic statics. Okay, bye-bye.